everyone, welcome to our presentation, the Fibonacci, Patterns in Nature and Numbers. Let's take a quick look back in time. The Fibonacci sequence was first introduced in Liber Abaci, or the Book of Calculation, written by the Italian mathematician Leonardo of Pisa, who we know as Fibonacci in the year 1202. In his work, Fibonacci used a rabbit reproduction problem to show how populations could grow over time, using simple math to model life. But did you know that this pattern existed even earlier? Ancient Indian mathematicians like Pingala and Virahanka had already described similar sequences centuries before. Over time, the Fibonacci sequence became connected to the golden ratio, approximately 1.618, a number that appears again and again in nature, art, and architecture, symbolizing balance, proportion, and beauty.
So, what exactly was the problem Fibonacci posed? He asked, how many pairs of rabbits will there be after n months if each pair produces a new pair every month after the first month of maturity? His goal was to find a mathematical pattern, a formula that describes how the rabbit population grows over time. So, this simple question led to one of the most famous sequences in mathematics, one that connects directly to the world around us.
Polya's 4 steps to problem solving. To understand Fibonacci's reasoning, let's use Polya's 4 steps to problem solving. Step 1. Understand the problem. We know one pair starts. Rabbits mature in 1 month and reproduce every month after that. The unknown is the total number of pairs after n months. Step 2. Devise a plan. We can find the pattern by listing the number of rabbit pairs each month. We notice that each term equals the sum of the 2 previous terms. Step 3. Carry out the plan. Let's track the growth. 1 month is equal to 1 pair. Month 2 is equal to 1 pair. Month 3 is equals to 2 pairs. Month 4 is equal to 3 pairs. Month 5 is equals to 5 pairs. And month 6 is equal to 8 pairs, and so on. The pattern rule becomes clear. F of n is equal to f of n minus 1 plus f of n minus 2 times f of n is equals to f of n minus 1 plus f of n minus 2, with f of 1 is equal to 1 and f of 2 is equal to 1. Step 4. Look back. We can check the rule with a formula called Binet's formula. And here's a fun twist. What if reproduction started after 2 months instead of 1? That would lead to a modified Fibonacci sequence.
Now that we know how it works, let's explore why Fibonacci is everywhere. The Fibonacci sequence works in a repeating pattern where each number is made by adding the 2 numbers before it. It goes 1, 1, 2, 3, 5, 8, 13, 21, and continues forever. This sequence leads to something amazing called the golden ratio. When you divide a number by the 1 before it, you get a value close to 1.618, which represents natural balance and pleasing proportion. You can find Fibonacci patterns in different areas of our world. In nature, you see it in the spirals of seashells, the arrangement of petals in flowers, and even in pine cones. Nature uses this pattern because it helps things grow efficiently. In art and architecture, artists and builders use the Fibonacci proportions to make designs look balanced and pleasing to the eye. It creates that perfect symmetry we naturally find beautiful. In computer science, Fibonacci is used in coding and algorithms, especially in solving problems step by step or recursively. It helps programs run smarter and faster. In finance, traders use Fibonacci ratios to predict possible price movements in stock market. So, Fibonacci isn't just math written on paper. It's a pattern that shapes growth, design, and beauty in the world around us.
The Fibonacci sequence proves that simple mathematical rules can create complex beauty. It connects mathematics, nature, and art. reminding us that math isn't just about numbers, it's about patterns, creativity, and discovery. Through Polya's process, solving problems becomes more than just finding answers. It's about thinking systematically, exploring creatively, and observing carefully. This sequence also reflects patience and progress. Each number builds on the ones before it, showing that growth takes time, whether in nature, knowledge, or creativity. Ultimately, Fibonacci's work deepens our appreciation for the interconnectedness of the universe, from the spirals in a sunflower to the proportions of a painting. It's a beautiful reminder that mathematics is everywhere, hidden in the rhythm of life itself.